Okay, good. We're recording again for part 2. Okay, here, so the uranium that breaks down, sometimes it's kind of like we think of uranium like atoms as if they're a bunch of like little small Velcro balls or magnetic balls that are all connected. Have you ever made a ball of sand at the beach? Okay, even if the sand's wet, there's a certain size that you can do, and then beyond that size, it just starts falling apart, no matter how hard you try to keep it together. That's exactly what happens with atoms. There's a certain size beyond which, when you try to keep an atom together, it just falls apart. Now, imagine that when that falls apart, maybe it falls apart and some of the water inside evaporates or something. So when you measure the mass of your sand ball before it fell apart, it gives you a certain mass. Then it cracks open and you measure it again. Now there's less mass than before. That's what happens here. That less mass became energy. Because when that atom breaks apart, it releases energy. Now, of course, we know this, right? Because what do you use that for? Yes, nuclear reactors, nuclear bombs. All right, okay, let me see. Okay, we did atomic theory, talked about photoelectric effect, kinetic energy. Oops, you know what, I need to talk about one other thing before we get into decay, which is our last topic. Back on kind of the wave and energy part, I need to talk about the energy, ionization energy. Anybody here take AP Chem? Did you guys talk about ionization energy in AP Chem?
Yeah.
Okay. What did you learn?
Ionization. Is that the one where like the electron wants the other electron? And so it's not. Oh, hang on. It's the energy that takes to remove an electron.
Yeah. Okay. So there's like these levels, right? Like all these levels going up. And if you want to kick an electron up to another level, right, then, is that E1 or E0? No, okay. You have to you have to give that electron a certain amount of energy. This E1 is equal to, I think it's 13.4 electron volts. An electron volt is a specific amount of energy. You see how this is all connecting now? Here comes a photon. Its energy I can calculate by what? How do I find the energy in a photon of light that is a specific wavelength? Yes, just HF. E is HF. Right? That's the first equation, the first thing you see. Right? So if you see anything about light being converted to energy, or if you're in the 6th question on the free response, that's when you use that special little box. And if it's got a photon coming in at a certain frequency, boom, Planck's constant. So I know exactly how much energy this has. Bam, it comes in. This thing gets absorbed. I should be able to calculate how many levels this goes up. Because this is 1, 2, 3, 4, 5, 6, whatever, 7. Right? I just plug it into this equation. How many levels do I want it to go up? Plug that number in. 13.4 electron volts is E1. Boom! And I can tell you exactly how far up that thing is going to get kicked. Right? Or if I told you that an electron started at 5 and dropped down to 2 and then released a photon. And released a photon, what would be the frequency of that light? Do it now.
How much the electron volts?
It tells you on your formula sheet what an electron volt is. somewhere. I swear it does. Okay, there it is. Oh, it's the charge of an electron, but in joules. I forgot about that. An electron volt is the charge of an electron in joules. What was it?
3.6 times 10 to the 14.
And that's in hertz. Okay, so John, how many levels does this thing drop? 5 from 2, right? 5 down to 2, that's 3 levels. Everybody cool with that? Now just plug it into the equation. So it's 1 over 3 squared, so 1/9 of 13.4 electron volts. Okay? So whatever that 1/9 becomes, is that 1.2 or 1.1 or something? What is it? Oh, 1.5. Yeah, okay. So that, like, it becomes like 1.5 something, right? Electron volts. Then you can convert electron volts to this. Because this is so many joules per electron volt, so you just multiply them, right? And then you get some, I don't know, whatever, some other giant amount of energy in joules. Okay? And then you use this, and you say F is E over H. E is what you just calculated. So you divide whatever you got, this energy, in joules by H, and then that's going to give you the frequency in hertz.
File's actually right.
You got it too? Sweet. And then, now, so we said this. Now, find the wavelength of that energy. What is the wavelength of that energy? Did you get like 1.2 times 10 to the minus 6? What'd you get?
8.7 minus 7.
Okay. What speed did you use for V equals F lambda?
Speed.
So V is F lambda. In this case, it would be C. So lambda is going to be C over F. So that's 3 times 10 to the, oh, I did it wrong. I did 3.6 over 3. That's why I got 1.2. 3 times 10 to the 8th divided by 3.6 times 10 to the 14th. So what did you say? It's 8?
8.
Okay, that makes sense. Because 3 divided by 3.6 would be like 0.8 or something. So yeah, so 8 times to the what?
10 to the minus 7.
Okay. So we get 8 times 10 to the minus 8 point what?
8.3.
8.33. So that gives us 833 nanometers. That would be to the minus 9. And that puts us slightly, that's infrared radiation. Ding!
Isn't that 83?
What'd you say?
It's the negative 7.
Yeah.
So
A
it's
nanometers is minus 9, right? So I was bumping up 2 decimal places to be able to call it a nanometer, just because I remember that light is 400 to 700 nanometers. Purple is 400, and 700 is red. So if it's 833 nanometers, we're on the low end or the long end of infrared radiation, probably moving towards microwaves. Cool. See, you just calculated from an electron dropping energy levels inside of an atom to like actual electromagnetic radiation coming out. And it's just using those equations that are there. So if you just look at those 4 equations, or 5 or whatever, Oh yeah, these 4 equations, and you know what they're for, you can figure out everything. Okay? So, E equals HF equals PC. This is the energy in light, the energy in electromagnetic radiation. So make sure you write this down on your formula sheet so you know. Is this recording?
Can you say it again?
Yes, it is. Oops. Okay, E equals HF equals PC. That is just telling you the first equation is how much energy is in light. Okay? So it's energy equals Planck's constant times the frequency. Right? And that's momentum times the speed of light. Then you've got the photoelectric equation. The photoelectric effect in your head should, when I say photoelectric effect, from now on, what are you going to think of?
Like,
Okay, I hope the first thing that you think of is a solar cell. Because that is the classic everyday example of the use of the photoelectric effect. Now, when you reverse the photoelectric effect, what can you do? Think of the dentist's office and the X-rays, right? The non-radioactive material using X-rays. So this equation, remember, is the kinetic energy of the expelled electron is equal to the energy of the light minus the work function. So you can think of it like this. The speed at which you leave your house is equal to the energy of your breakfast minus the energy it took you to get out of bed.
Say that again?
So HF is like your breakfast energy. And then you subtract the amount of energy it took you to get out of bed, right? And so you got out of bed, you're negative, I hate life, I hate everyone, screw you. And then you ate some breakfast, now you have energy, and then the leftover between that is what's going to get you out of the house. Kind of, I don't know if that helps, but whatever. Right, that's Planck's, or that's the photoelectric effect. Then, this is the de Broglie wavelength. The de Broglie wavelength is the wavelength of everything. Anything and everything. Because anything and everything can have momentum. De Broglie, like D. Well, yeah, I'm going to write it when I talk about the final thing here real quick. And then, of course, the theory of relativity, right? That just says energy, the energy in matter is connected by this equation. So if you calculate, let's say Helen's eraser, okay? This eraser probably weighs about 10 grams. Using this equation, calculate how much energy is in that eraser. Equals MC squared. Go ahead and do that. Oh my goodness, you don't need a calculator. Think.
Oh, but C squared.
That's 9 times 10 to the 16. Right? So it's 10 grams, so that's 0.01, right? Yeah, so 9 times 10 to the 14 joules. 9 times 10 to the 14 joules of energy. That is kind of huge, right? The largest power producing plant in the world, I think, produces a gigawatt, which means that's 1 billion joules per second. Okay, that's 1 times 10 to the 9 joules per second. So it would take that power plant, what do we say? 14? It would take it 100,000 seconds to produce the energy that is in her eraser. Okay, so that's the equations. Hopefully you have a grip on what those things do. Let me write down, this is how you spell de Broglie for the de Broglie wavelength. Okay.
So do we have to memorize the ionization energy?
If you just remember that, like, it takes, you know, I have seen problems like that where they did that, but I think they told you the ionization energy equation. But it's not that, it's just, you know, 1 over the square of the change, so. Yeah, and the constant, I don't think that's, yeah, well, they gave it in the problem, I think. So, okay, so let's talk about decay real quick. There are 3 types of decay. alpha, beta, and gamma. I know that's not a good gamma, but whatever. This is this particle. Okay, that's a helium atom, basically, that gets decayed. This is an electron, and this is gamma radiation. And no, sadly, exposure to gamma radiation will not turn you into the Hulk. It will, in fact, just kill you. Yeah, it kind of looks like a funny little R. Alpha particles can be stopped by clean suits. You know what I'm talking about? Those plastic. Basically, they can be stopped by anything. Like an alpha particle won't even go through your clothes, right? If you have reasonably normal clothes on. So as long as you don't breathe, like if you have a filter over your mouth and you wash your clothes after being exposed to alpha particles, you're fine. You'll be okay. Beta particles can penetrate through paper and light clothing, and so they'll hit you. And gamma, it goes just right through, and it screws up your DNA when it goes through. So, lead. That's what they do. All right. So if we talk about an alpha decay, here we're going to talk about polonium-210-84, and this is going to lose an alpha particle plus some amount of energy. Now, what goes right there? Figure it out. You don't have to know the element. In fact, I'll tell you, it's plumbum. Anybody know what that element is? It's not plumbum. Yeah, it's lead. Pb is lead. Plumbum is the Latin name for lead. Come on, look, do the math. What's going to go right here? Do you see it? If this is 210, where did that come from? From this, which means this is 206. That's it. You see it? That is an alpha decay. That's all it is. Okay? And then what happens is, like, if there's some sort of loss of matter, it will come out in this form of energy. Then we have a beta decay. Here's a beta decay. I think this is thallium. It's TO. No, titanium is TI. I think it's whatever. I think it's thallium, but whatever. Let's see if we can figure that one out. Oh, the element is once again plumbum. Well, that's not good because I told you the answer then. All right. It's 206.82. Good. Do you see how that worked? What did it lose? What did the thallium lose? An electron. And what got changed in a beta decay? Where did that electron come from? Where is there something? Because what did this gain? Oh my gosh, I'm going to go tell this drama to people. What did it gain from here to here? A proton. It gained a proton. If it gained a proton by losing an electron, what do you call it when you add a proton to an electron? If you combine those two, what is that thing? A neutron. So this has a neutron becoming a proton plus an electron. That's what happens in a beta decay. And there will be these weird decays where, like, it cracks, like you're losing matter and your atomic number is getting lower. Then you have a beta decay, your atomic number actually goes back up so that it can crack again and become something else. And then gamma doesn't really, gamma is just like this. It comes out like that. Okay, and then finally, just so we can understand how these things work, fission and fusion and fusion. These things, obviously, I need to get some sleep, but I'm not gonna. I apologize now for my behavior tomorrow. Yeah, no, I'll tell you what. Huh?
Just take a nap.
Yeah, I can't, because it's not fair to my life. It's like, I'm going to watch a movie, I'm going to go to bed now, thanks for dinner. No, I don't want to be a jerk to her. Let's be a jerk to you. What's that? No, I'm watching it tomorrow night. So I'm going to see it twice, 2 days.
Wow.
Okay.
What if it sucks?
What if it sucks?
Yeah, what if it sucks?
I don't think it could have gotten the reviews that it did.
I'm just saying, what if it did?
Well, then I wouldn't do that.
But that's international.
Yeah, like yeah, that's true. Like frogs are weird. So who knows? Just kidding. French people are wonderful.
They wouldn't say this, right?
Okay, so fusion and fission. All right, the difference between these, fission is what we just saw, right? It's breaking stuff. Right? You can start with plutonium and it breaks down. Fusion, you can do something like this. I believe that's it. I'm gonna check my notes. Yeah. This. Okay. Yeah, that's a neutron. Oh, what? Right? This is what the Germans were working on in World War II. This is what we were working on. This is easy. Right? This is very hard. This one, about 45 pounds of plutonium, and you get the equivalent of 25,000 tons of TNT. That's a lot of nerds right there. That's a lot of nerds. All right, it's about 25,000 tons of TNT, of dynamite, basically. Okay? So this is what we dropped on Hiroshima and Nagasaki, and it destroyed the whole city. Just as a side note, one of the reasons why that was so effective is because the Japanese built their cities out of wood. Everything was built out of wood. That's why it was such a devastating thing. If their buildings had built out of concrete, mortar, and all that stuff, it might not have been a big deal, or as big a deal. Still would have been a big deal. Anyways, so 25 kilotons right here, right? Yeah, they did have some rips.
Just wondering, in like a nuclear bomb attack, if you were like in a shelter made out of lead, would you be safe from it?
Yeah, there's plenty of shelters where you'd be fine. Yeah, but you have to be a certain amount on the ground. Depends if you get lucky or not. Because nobody will use this kind of bomb anymore. This is what terrorists would try to use because they could make some. This is why we don't want nut jobs getting uranium enrichment facilities. Okay, because Kim Jong Il has this. Oh, no, he doesn't. He's dead. Kim Jong Dum or whatever his summary is. And this is what Ahmadinejad, the guy from Iran, he's trying to make that. But this is the key. This is something called deuterium, and this is tritium. These are both isotopes of hydrogen, right? When you combine these two, you get a fusion reaction. 25 kilotons on the order of 4 megatons. Okay, notice the difference.
That's a hydrogen.
Yes, that's a hydrogen bomb. That's why it's called a hydrogen bomb, right? So the hydrogen bomb is basically what prevented war in Western civilization all through the 50s, 60s, and 70s. You could argue that it almost caused a war from the, what is it? Khrushchev? Yeah, Cuban Missile Crisis. But beyond that, it's kind of like what's prevented war from happening because of mutually assured destruction, right? But this, yeah, so one of these bombs produces, what did I say, around 4,000 kilotons. No, 4 million kilotons. Yeah, it's did I say 4 million? Yeah, 4,000 kilotons. This is 25 kilotons. Right?
4,000?
Yeah, this is 4,000 kilotons, and this is about 25 kilotons.
I don't think you
Yeah. It's not nobody's going to ask you that. But you can see the difference is one of these above downtown Los Angeles kills most of the people in the San Gabriel Valley around here. It liquefies. Like downtown Los Angeles is gone. All the buildings gone. Within an instant, as soon as it goes off, there'll be a speed of light flash. That if you're standing in San Gabriel and you're facing that way, boom, you're blind instantly. Right? Probably third-degree burns on your face, on any exposed skin. Out this far, the shockwave would take a while to get here, but it would still destroy most of this stuff. Downtown LA would be just literally, there would be nothing there. Because then shockwave, because usually these bombs are detonated in the air. These bombs are detonated on the ground. The problem it's worse when you detonate in the air. Because then the shockwave hits a bigger area. And then what happens is it goes boom, and it pushes all that stuff away. And then all that stuff comes back. And the thing is that all the radiation, all the alpha particles, all the crap that it irradiated gets pushed away. And then it creates a vacuum because it pushed all the air away. And then all the air comes rushing back. And when it rushes back, it scoops all that radioactive material together. And when it claps together, it can't go down. So it has to go up. And then boom, it shoots all that radioactive material up into the upper atmosphere. And then because the pressure is less up there, what does it do? It expands. And you get a mushroom cloud. That's how mushroom cloud comes from. But yeah, so hopefully this is not useful for anything except killing people at the moment. There have been fusion reactions on the Earth, but none of them have been sustained to produce energy. This is what we use for nuclear energy. All right? Okay, so we've gone through all the equations. We've gone through the logic, the basic logic that you need to know. You know that this is from nuclear reactors, and that is pretty much it. Thank you very much.